Were we on?
Now we are now.
We are now, okay. So I'm going to go over a few basic things before I actually do the problem, and just make sure we all know the rules, because we've come up with a lot of results so far, but we haven't really tied everything in, and it kind of gets tied in. So one of the things we know, okay, arc length, which doesn't seem to have anything to do with this, we know it's, all right, the integral, I'll just say from A to B, of what? Of dx dt squared plus dy dt squared plus dz dt squared dt. But it's this portion. Now, this is s of t. Okay, well, actually, let me do it this way. Without the a and the b. Okay, it's now a function, and then I would evaluate it at the endpoints. So if that's a function, the only way you can get s of t is to integrate ds dt with respect to t. Everybody understand that? That's the only way you integrate the derivative. So that means that this quantity right here, the square root of the sum of the squares, is generally referred to as the arc length parameter. Okay, that's what it's usually referred to in any textbook, because that's the thing you integrate to get the arc length. Now, if I have r of t equaling x of t, y of t, z of t, then I know that the velocity is the derivative of this. Okay, and the magnitude of the velocity vector, then I know is the sum of the squares under the square root. Okay, piece of cake. What's another name for the magnitude of the velocity? Speed. Speed. Is there confusion between speed and velocity in life, and people in general? Yeah, because if you're not a math science person, do vectors really matter to you individually? If you're not, no, of course not. So when someone says, how fast are you going? You tell them how fast you're going. And they say, oh, what is your velocity? Most people just in regular speaking treat velocity and speed as the exact same thing. But we know in math and science it's not exactly the same thing. Velocity is the vector. Speed is the magnitude of the velocity vector. So there actually is a separation for what we're doing, okay? Because a velocity vector isn't a number, because it also has direction. Oh, okay, so this I know is speed. Let's put in words. This is speed. Okay, why is that important? It's the same thing, isn't it? The arc length parameter and speed are exactly the same thing. So that means this is a ridiculously huge and important identity. And the reason this is huge is there are some formulas where you want to leave it in this form, because maybe you want to differentiate it again, or integrate it. Other formulas you want to leave it in this form because it was fairly easy to work with and fairly easy to find. These are interchangeable in all of our formulas. And so one of the things, if you looked at the notes that I posted, I used both of them. It's out of convenience. For that particular formula, which one is going to be easier to work with? Okay? So if I'm giving you a result and I want to calculate something, I'm probably going to use this one because it might even be a scalar at this point. Okay? Does that make sense? Oh, okay. In other words, I want to use the magnitude of the velocity at a particular value of t. Ah, so that's, okay. Notation-wise, it's harder to write ds dt evaluated at a particular value.
I'm confused when you say, like switching between using ds dt versus the magnitude.
In a formula, well, I'll show you.
It's the same things, right?
They're the same thing, but in the formula sense, if I'm taking derivatives, let's say, and we do with the ds dt, I have to take another derivative. I'd rather take a derivative of ds dt. Oh, okay, then it's d squared s dt squared, second derivative. But to write derivative of magnitude of velocity vector, that's kind of an odd notation thing. In other words, it doesn't read as well. It's harder to interpret. So in the formulas themselves, we use these interchangeably, and I'm going to show you. So this is a little bit of background because we know these things are the same, and that's so powerful. Okay? So, hold on, I got all these notes spread out here. I want to make sure I'm grabbing the right thing. Oh, here they are. So now knowing that, okay, curvature. The notion of curvature is a fairly simple thing. Let's stay two-dimensional for a moment. We're in a 3D world, but I'm moving around, I'm driving in my car. But let's say we're driving on a flat surface. I don't even want you to think going up an incline quite yet. But I'm in 3D, but I'm driving around on the roads, okay? And we're turning at all times. In the simplest sense, and I say this in the videos, all motion is linear, perfectly circular, or somewhere in between. What do you think most things are? Somewhere in between. Which means, oh, the linear portion is described basically by the unit tangent direction. The circular is described by the unit normal, because that's where the unit normal points, and then everything else is some combination of the two, which we will see. So if I'm moving on a perfect circle, that's really nice. If I'm moving on a line, that's really nice, but those are the extremes, okay? So what curvature is how fast am I turning? So that's why the definition of curvature, excuse me, the definition of curvature is basically how fast is the unit tangent changing. Let me go, a real simple example. Okay, so if I said take small increments of arc length, and let's say these are all little unit vectors, would you say that it's the direction of my unit tangents aren't changing a whole lot right there? So in other words, the rate of change of the unit tangent with respect to the length of the arc is probably not huge. But now we get into here, right? You'd say, wow, it's changing really fast. So the rate of change of my unit tangent for each little unit of arc is a lot here. So we'd say the curvature here is probably a lot more than the curvature here. That's just from a simple notion of what it means. If I do, let's say that point right there, there is a tangent circle. You can always find a tangent circle. Similar to a tangent line, a tangent circle, right, is going to be tangent at that one point. So the tangent to the circle and tangent to the curve would be exactly the same thing there. But let's say here, right, that circle's probably huge. You with me? So we say the smaller the circle, the greater the curvature. Question?
Is the tangent normal equal to the radius of that circle?
Say again, the tangent normal.
Like the normal that's going
Yeah, the normal and the tangent aren't the same. They're orthogonal. Yeah. The normal vector is going to point towards the center of the circle. That's true.
Is that equal to the radius, or is it just pointing in the direction of the?
Well, hold that thought. There is a connection with the radius of the circle. And the connection is actually quite simple. The bigger the circle, the less the curvature. The greater the radius, the less the curvature. There's actually a reciprocal relationship. The curvature, believe it or not, when you actually calculate, is equal to the reciprocal of the radius. Now, when you're on your street, you're parked on the street. Does anybody have a car where you can just simply do a U-turn without having to do the 3 or 4 or 5 point turn? Yeah, my son has a little Toyota, he can do that. What do we always say when we describe that car? We say it has a real tight turning radius. Yeah, we say things like that. What the heck are we doing? We're actually using this mathematics verbatim. Oh, it has a really small turning radius. That means it can turn a really small circle, so it can work with great curvature. So that's when you're on the windy road, okay, it's better than a big lumbering, truck or something for the tight curves. So if we understand that's the general means of the curvature, then the definition of the curvature, basically, big K is the magnitude of dt ds, except we don't describe any functions dt ds. We do everything with respect to time. But that's the definition. Oh, how fast is that changing? And I want the magnitude. So then just simply using chain rule, which I show in the notes, really simply, this ends up being 1 over this dt dt. Okay, that's just simple chain rule. dt ds, dt dt, ds dt. Now, this comes directly from chain rule. Oh, now here's where I might swap out this, because if I have to take another derivative, this is difficult to take a derivative in this form, isn't it? So this is where, from a formula standpoint. Now, but if I have these values, these are magnitudes. This is a quotient of magnitudes. That's really, really simple to work with. So the first version of curvature, and you could write this as a quotient because these are both scalars. The first version of curvature is just this. Okay, piece of cake. Right, that's nice. But that might be gnarly because this vector here, more often than not, is probably not that easy to find. If I'm going on a perfect circle, that vector is easy to find. If I'm not, that vector can be a real mess. So then I show you, if you keep going, again, this is all derived in the notes when we take derivatives and we manipulate. But this also comes out to be the magnitude of V cross A over the magnitude of V cubed. And not because I'm telling you this, this was derived in the video, this is derived on the notes, but you don't necessarily have to know the derivation. And so it's good to look at it and say, oh, that makes sense. I see where everything came from. It's really the result. So now you have exactly two ways you can calculate curvature. If it turns out the function you're working with, the R of t you're working with is easy to work with, then you're just going to do this. But if the one you're working with, if it's steadily getting more complicated, you're probably going to want to do this. That's it. So you actually now have a choice. And again, that's what all of that stuff in the notes, the derivations. Now, since all motion I said is either linear, circular, or some combination, if I'm moving on a line, there is no circle of curvature. So we'd say our curvature is 0. Yeah.
In terms of the bonus question for the quiz that we just turned in, which one would you have suggested that we use?
Probably the direct method, because things are going to cancel really nicely in that one.
Okay.
In that one, not always. Now, why? Because when you see sines and cosines, derivatives tend to be really friendly. But I'd use, product rule and stuff. But because every term had an e to the t, I can also factor. And then you see that I'm going to get tremendous cancellation. So that one on the quiz, I would definitely go this route.
Okay.
But we'll do an example, and the example that I do in the notes, I go the other route. I do both routes, but I show you, well, the other route, man, it's a little bit easier. Okay? Now understand, first of all, you rarely express curvature as a function. You generally express curvature at a particular point. So if Samuel says, I just drove, cross country. Oh, how fast did you drive? He drove for 50 hours. It's like, I didn't drive a constant speed. No, people are like, oh, how fast were you going at this point in the trip? Whoa, when you passed that landmark, how fast were you going? That would make more sense, wouldn't it? Not how fast were you going for the entire trip. That question doesn't even make sense. What, your average speed? What am I asking you? You stopped for a bunch, you slept overnight, you weren't moving at all. So with curvature, we don't say, what's the curvature for the entire function? Because it might be different at every point. We say, what's the curvature at that value of t? Therefore, curvature, the answer to a curvature question is almost always going to be a scalar. Okay? So that's one of the reasons we like this, is because we found v of the number, a of the number, did the cross product, we got a vector of scalars, and then we took its magnitude, in other words, scalar over scalar. Way simpler. What a lot of folks do, though, they make the mistake if they do everything in function terms, it gets big and ugly and nasty, and then when they're all done, then they evaluate. Remember, the rule of thumb is, you don't evaluate until after you're done taking derivatives. But if you've got a of t, there are no more derivatives to take. That's the last possible derivative you could have taken. So once you've found the acceleration vector, now you can start evaluating things. And that's a good strategy, because otherwise, some of you may have found you did this. You kept things as functions of t, and then v cross a got really big, didn't it? Did anybody do that? You filled the page, and then you did all this, and then in the end you got some simple answer, and then you look at the key and go, oh, Mr. Brown evaluated it before he took the cross product. Ah, it's really small and simple. Because you're doing it at a value. And you're almost never going to be asked to do this as a function of time. Because again, that's like saying, how fast did you go for your entire trip? No, how fast were you going at that moment in time? Okay, so with that said, the other thing is, acceleration now can always be written as a linear combination. Remember, linear combination means scalar multiple of one thing plus scalar multiple of another thing. As a linear combination of the unit tangent and the unit normal. And so what we call the scalars, we don't just randomly call them a and b or something like that. We say, no, we're going to call this the tangential component. It's a with a subscript of t, and that's a scalar. That's not a vector. T is the vector. This is its coefficient. And this we cleverly call little an. So this is called the tangential component, the normal component. If I am moving on a circle, by the way, 2 and 3 dimensions, it is the same thing. Even if I'm moving in 3 dimensions, we still calculate curvature exactly the same way. Okay? If I'm moving in a circular motion, even if I'm in 3D, if I'm moving on a circle, can anybody tell me what AT is?
0.
0. Because it means all the motion is in the normal direction, and the normal always points to the center of the circle of curvature. Okay, so now if that's the normal and that's the tangent, then moving this way is some combination of these two, isn't it? Okay? If I'm moving linearly, I'm moving on a line, even if it's just for a short period of time, then what's AN?
0.
0, because there's no deviation. And most of the time, neither one of them are 0. Most of the time. You with me? How many here ride a motorcycle or even a bicycle on a regular basis? Motorcycle riders, anybody? So I always have fun with the motorcycle riders because they always laugh when I do this. So you're riding a motorcycle, you have your helmet, and you're riding a motorcycle and you're ready to make a turn, so of course you drive like this. And bicyclists, you do the same thing, don't you? You put on your blinders like the horses, right? And as you do it, you start your turn, and then just pray as you turn that you don't get hit by a car or something. Or when you're riding and you're ready to turn, you go like this. Does anybody turn their head? Yeah, probably. It's actually simple physics. I proved this, I think I did on the video when I talk about the San Jose airport, that helix. I was just there a couple weeks ago and it cracked me up. Guy in front of me got stuck and he actually scraped his car, which is funny because it's a rental car. What way do you look when you're riding in a bicycle or a motorcycle? Probably less so in a car. But when you're riding a bike or a motorcycle, which way are you looking? Are you looking straight ahead? In other words, are you looking in the direction of the tangent? No, because you'll get in an accident the moment you turn. What direction does your head always turn to? Always turns in the direction of the normal vector. In other words, you're getting ready to turn, your head automatically turns because that's where your acceleration is taking you. And more specifically, you're turning in the direction of the acceleration, which may not be the normal, somewhere in between. The tangent vector, when you hit the banana peel in space, that's what I always call it. You're moving through space and you hit the banana peel in space. Which way do you slide? In the direction of the tangent vector. That's also the direction of the velocity. But where are you actually going? You're going in the direction of the acceleration. You're not going in the direction of the tangent vector, right? Because if I was going in the direction of the tangent vector, I'd still be going this way. Oh, the acceleration determines where I'm going to be next at all times. That's why the acceleration is so important. So it's this combination. Now, we know how to find this, we know how to find this, and this one, this is never hard. This can be very, very difficult. It can be. But now I'm interested in these guys. Remember, when you go outside, we don't describe vectors this way anymore, do we? We say, go that way, you know, this far, or go that way, this far. So if I said I'm moving around space, as I'm moving through space, let's call the orange my tangent vector. So I'm moving through space, okay, unit tangent, unit normal. That will describe my motion in general. Now, these are both unit vectors. Oh, so if I'm mostly going straight, then that would mean that this coefficient is bigger than this coefficient. If I'm mostly turning all over the place, then this coefficient we'd expect to be bigger than this one because these are both unit vectors. Agreed? So now, how do I find those two guys? We find those two, where is one? No, it's here. We find those two guys, again, I went through all of the nasty derivations and things like that to show you how to do it. Again, I don't need you to memorize the path, but the path should make sense to you. Because all we're doing are dot products and cross products with some maybe product rule involved, okay? But with all of that, the AT, let me just write the summaries real quick. The AT can be found a couple of ways. The first thing is, AT is the derivative of the speed. Ooh, that arc length parameter. So that dsdt, which would be a function of time, okay? If dsdt is a function of time, then this is what AT is. Now, that isn't necessarily the easiest thing in the world to find, okay? We also have a backdoor. It's v dot a, write everything down, over the magnitude of v. Now again, understand this means they've already been evaluated at the time in question. So you wouldn't want to write this as a function. You'd say it's the second derivative evaluated. It'd be v dot a over like the v evaluated. You can leave it as a function of time, but as we all know, this can get really messy, right? I can't evaluate it at that point. Which one is easier? It depends. Now, if I'm moving on a line, okay, That doesn't mean DSDT is constant. No, that's, so you gotta be careful on that one. If I'm moving on a line, I can be speeding up and slowing down on the line. Okay, so a lot of folks make the mistake of saying, well, if you're moving on a line, isn't your acceleration constant? No. No, if I'm running and I'm jogging and I speed up and I slow down, does everybody agree that no, it's not constant? So you want to be careful on that one. And then the AN on this one, AN, so which version do I want? Oh, AN is, this is awesome. It's magnitude squared times curvature. And again, I can use this because it's the same thing. Again, it depends where I am in the problem. These are exactly the same thing. Okay? Now, is this easy? Well, this is easy if K was easy to find. But if K was not easy to find, okay, then the other version, my backdoor version of AN, where do I have that on here? Well, that is the definition of AN. I've got this somewhere, hold on. Oh, but we know what K is, okay? Where'd I have K? So if I replace the K, see this? And then what does this become? Two of the V's cancel. This becomes magnitude of V cross magnitude of A simply over length of V. And again, this is a backdoor way. Is it shorter? Might be. Now there are folks who say, you know what, I'm always going to use these versions. I'm always going to use those, and that's okay. But they're not always the fastest.
Would it be V as a vector squared? Or the magnitude of V as a vector?
Yes. Yeah, that's, now, because this is what this is here, knowing there's a backdoor way to find K, if I just replace K with this, then a bunch of those V's magnitudes canceled in there. So again, this might be the easier of the two. This might be the easier of the two. I can't tell you it's going to be from problem to problem.
And for the magnitude of V cross A over the magnitude of V, that's evaluated here, right?
That's
Evaluated at the...
again, yes. You would say, once I've found everything in the problem, by the way, you don't evaluate V and then take its derivative.
No.
You take the derivative of V to give you A. You take the derivative of the unit tangent vector to give you the dt. But now you're to the point where, say, I want to start answering the questions. I want to start evaluating things. Evaluate before you do your dot and cross products will make the problem a lot less nasty. And those of you who, again, waited till afterwards, you realize how big and enormous that problem became, you still got the same answer in the end if you didn't make any mistakes, but you can really save time, because now I'm saying at the value t equals 1 or t equals 5 or whatever, find the curvature, you say, okay, then technically what I'm doing is v of 5 cross a of 5. So now I have a vector of scalars. Way, way, way easier to work with. Okay? Now there's a couple other little minor things. These are at right angles. Do you agree? So I'm moving through space, and here's my AT times the tangent vector. So maybe AT is 10. So it's 10 times the unit vector, and maybe AN is 5. Okay, so I went 10 in this direction, 5 in this direction. Great. But they're at right angles. So think about this for a moment. If these are at right angles and I'm adding them together, then you can think of that guy right there . These are scalars. I'll just put your name on everything. Okay, if AT and AN are scalars, but the vectors they live on are at right angles, then this is the magnitude in the direction of t, this is the magnitude in the direction of n, and I have a Pythagorean relationship. Is that useful at all? This is the easiest and maybe the most important check there is. Because this means that AT squared plus AN squared must equal the magnitude of A squared. So a lot of folks will say, you know, I'm pressed for time when I found AT, and by the way, the magnitude of A is one of the easier things to find because you're evaluating A at a scalar. And A is never going to be hard to find. things tend to get smaller, not bigger. So you might say, well, I already found this one, and I found this one. Can I just use my Pythagorean theorem to find this one? Yes, but it's always a little bit dangerous to say, I'm going to use my prior results to find the new guy, because what if either one of those had an error? Then it means all the numbers are incorrect. I don't do it that way. Here's what I do. I independently find this and this, and then I use this as my check. Way better. Because then if it checks, then it's absolute certainty that everything is correct. If it doesn't check, then you know it's not correct and you can fix it. But if you calculate a value and then use the calculated value to calculate another value, if the first one's not correct, then the second one's not going to be correct either, as you know. So I like to use that as my check. Okay? Does everybody follow that? It's actually a little bit safer to do it that way. And these aren't really time consuming because you're using the same information over and over again. So as I move through space, the most important thing, this is sort of the culmination of all the stuff we've done, is to get the answer here by finding all the pieces of the puzzle. Okay? Any questions so far? So I wanted to go over this. By the way, I kind of laugh. I've got an email from my chair and from my dean last night saying they sent me a copy of the 2023 calendar and say, see, they have the Juneteenth as a holiday for 2023. And then I sent them the district copy of the 2022 calendar and the district portal for all faculty that work for the district. And it says in clear English, the only holiday this summer is July 4th. Every person who works for the district has two calendars, both of them say, but the students got word that, and I thought it's funny, and then people are going, well, everybody knows it's a federal holiday. My wife's a high school teacher at a public school. She worked all day yesterday. There aren't that many places that closed, and the district closed, and I feel kind of embarrassed, but you know what? Nobody that works in the district had any reason to think it was a holiday because we were the only class meeting. That's why there's no email trail. There has never been an email from the district to any person who worked in the district saying yesterday was a holiday. So you were just supposed to know, apparently. But not everybody knew because I was here and there were a lot of people actually showing up. right, Quinn? Where's Quinn? Yeah, we're all here, right? Sam was here. I'm kind of annoyed. I'm not embarrassed. I'm annoyed that when they sent me a copy of the 2023, say, see, it's right here. And I sent them exactly the link to the 2022 and said, seriously? Yeah, great. They've announced that next year there's a holiday. Never bothered mentioning this year, but you guys apparently, a lot of you knew. How did you guys, or when did you guys know?
I thought 1 a.m.
Thursday? I think, Samuel, you were showing me on your portal looks identical to my portal, except it had the one additional date on it. And I showed Sam mine, it's like, seriously, they let you guys know. But just like I said, I know a lot of people in education and none of them had yesterday off, so that's, it's what it is. So it's a new thing. But the good thing is you guys were so on top of things. And I gotta tell you, I'm kind of impressed that the quality of the work so far, and if you've been in my classes, you know I don't give out compliments freely, but the quality of the work right now has been just tremendous. And the attention to detail. You're in such an awkward situation having a partially online class anyway, but I think you guys have gotten kind of used to it from other sources anyway, that you can navigate through this. But I don't like you having to do too much on your own. That's why I wanted to do this, kind of tie things together. Now, today's lecture material is the first lecture to exam 2, and it's actually from a conceptual and difficulty standpoint, not a very high level. The next lecture, tomorrow's lecture, is one of the most important for the whole semester. Not because it's hard. Tomorrow we're going to learn how to do derivatives in higher dimensions. It's not hard, but it's the first time you will have done that. So it's really, really, really critical information, and we're just going to be doing it over and over again. And you're all going to be really good at it, and then we do more of it after the test. So we have a lot of time to play with. So I want to take a problem and just kind of look at it from beginning to end and show you some of the things you can do. So I said, basically speaking, there's really 2 types of motion. There's motion that's circular, and we're never going to deal with just linear motion. That's boring. So, well, what would linear motion look like? All scalars, right? No, I don't want to do that. So let's consider r of t, I'm going to start with a simple one. R of t, let's say, is 8 cos t, 8 sine t, and let's say this guy here is, how about 14? So this is a helix. We talked about that before, right? I'm telling you that. You don't necessarily have to know that, but we've done one of these before. This would be a helix. It would be a very tight helix, and it's very interesting. So I want to describe the motion on this thing. What I'd like to do is answer every conceivable question about this one. Okay? This we love. We love this one. Right? This question is not going to present us with a whole lot of difficulty. So what we want to do on this one is do all the straightforward methods. So first thing we do, what's v of t? That'd be negative 8 sine t, 8 cos t, 4. What's a of t? That'd be negative 8 cos t, negative 8 sine t, 0. Interestingly enough, that means your acceleration is on the plane. It's not actually in 3D. Okay? That's why when I talked about the San Jose airport, when you're taking the rental car, and I'm serious, every time I fly into San Jose, I rent a car and I have to go down this tight helix. You're not looking up or down, you're looking perfectly sideways as you descend, or as you ascend when you're returning the car. It's interesting. Now, we would like to know what's the curvature, what are all the different pieces of the puzzle. So the first thing we need to find is the magnitude of the velocity vector. Now, let me just give you a value. Let's just say we want to do everything. Let's say everything I want to do at t equal, let's just pick a value. Let's say at t equal pi. So that means I'm going to have scalars at some point. Do I want to start evaluating everything now? No, because I still need to find my unit tangent, my unit normal. I need to find more vectors, which involves more derivatives. So I'll kind of wait. Now, I can evaluate each of these now. But when I take my derivatives, I got to take them of the functions, not of the evaluated things. Everybody follow that? So what is the magnitude of the velocity vector? Well, that would be the square, so 64 sine squared plus 64 cos squared plus 16 under the root. Well, that's 64, so I've got root 80, which would be, what, 4 root 5. Okay? And that number will probably show up. And by the way, you notice this is a constant regardless of the t. That's interesting. That doesn't happen all that often. So what is my unit tangent? Well, I take 1 over that, and I multiply it by this. Okay? So I'm going to put a 4 root 5 in each denominator. You can probably do that in your head. Or how about if I write it like this? 1 over 4 root 5 times v of t. And then that will be negative 2 over root 5 sine t. 2 over root 5 cos t. And then 1 over root 5, period. Now, if I did this right, this is supposed to be a unit vector. Square plus square, that'd be 4/5, plus 1/5, that's 1. That's a good thing. The reason you should always check that, not that you would do this, but you know somebody who would. They didn't multiply by 1 over. What did they multiply by? By 4 root 5. The most common error when it comes to this sort of work is people multiply by the magnitude rather than the reciprocal of the magnitude. I see that happen all the time. I see that happen in linear algebra. We understand everything, but when we actually executed, we forgot the reciprocal. So it was no longer a unit vector. It was actually longer than the original vector. Now, I need dt. There's a common misconception that people think this is the normal vector. This is not the normal vector. This is the direction of the normal vector. The normal vector is the unit vector in this direction. But it's actually very unlikely that this guy's a unit vector to start the problem. So when I do this, I'm taking this derivative. Okay, when I do that, I will get what? Negative 2 over root 5 cos t, negative 2 over root 5 sine t, 0. Now clearly that's not a unit vector, is it? The coefficients on the sine and cosine give that away. Now, when I'm finding the magnitude of this guy, you're going to say, all right, squared, so it'll be 4/5 cos squared t plus 4/5 sine squared t plus 0 under the root. Well, that's just root 4/5 or 2 over root 5. Okay? So far so good? So what am I going to do to find n of t? I'm going to multiply by the reciprocal of that times dt dt. Now when I do that, I will get negative cos t, negative sine t, 0. Is that a unit vector? Yeah, that's pretty obvious. That's a unit vector. Now, major thing. Maybe the most important thing so far. We haven't really had anything to check yet. Tell me about your unit tangent, your unit normal. Well, they have to be unit vectors, duh. Well, we checked they're both unit vectors. What's the more important thing?
They have to be orthogonal.
They've got to be orthogonal. How do you check for orthogonality in general? Dot product. And again, this is a high-end group, but that's the one area that most groups are deficient. They don't do the easy checks. They forget to check. Is it possible I have a plus or minus sign error? Is that possible? Yeah, that's probably the only true error that we know is a consistent error. We took a bad derivative, something went wrong, okay? Do the dot product, and what do I get? Positive 2 root 5 sine cos, negative 2 root 5 sine cos, and those add to 0. Right? Crowd goes wild, confetti everywhere. Well, not yet. That was a check, we're not done. But that was an important check. I now know my unit tangent is correct, I now know my unit normal is correct. Now the final answer to the question that I want to do is essentially I want to write a of t as a linear combination of that vector and that vector for this value. Okay. Now, are we done taking derivatives? Are there any more derivatives to take that you can tell? I think we're done taking derivatives. I think the last derivative we could possibly have taken is this guy. So this is probably the best time to start evaluating things. If I evaluate too soon, again, I may be taking the derivative of a vector of constants, and then I'm going to get the 0 vector. When you get the 0 vector, you should be very suspicious. I'm moving through space. Why am I getting a 0 vector? Oh, right, I got it. I don't need this guy, I need this guy. So what is v of pi? V of pi is what? By the way, some of us need to double check. Actually, not very many, but we had some, one of the quizzes you had to take the sine and cosines of pi. Sine of pi is 0. Cosine of pi is -1. We hit it. You got those backwards. Yeah, that's not a good error. It wasn't a common error, but it happened a few times. So I've got 0, -8, 4. Agreed? That's my velocity vector evaluated at pi. What's my acceleration vector evaluated at pi? Anybody?
800.
800, good. Okay, so we'll keep those in our back pocket because those are going to show up later. All right? Well, this was the same no matter what. We don't have to worry about that. That's not changing any. And how about this thing? What is... I'll write it right here. What is t of pi? My unit tangent evaluated at pi. 0. Negative 2 over root 5, 1 over root 5. And that's easy to tell now that's a unit vector, right? Some of those squares is clearly 0. Let's go to our normal vector evaluated at pi. What's that going to be? Our normal vector evaluated at pi will be 1, 1, 0. Ooh, this is nice. Is it pretty obvious that these are orthogonal? That's a good thing, correct? Now, what is our curvature? Well, we're almost there. We've got everything we need. Curvature at pi, well, you know what? This is interesting because This is a scalar. There's no t in this. This is a scalar. There's no t in this. Do you find that interesting? The two magnitudes that I need are both scalars. Why is that true? Because on the helix, oh, I'm just moving circular path and through. Oh, okay. Does that make sense why those would be constants? I'm not changing anything as I move through space. So what is the curvature? Technically it's curvature pi, but in this case it's just curvature. It's this divided by this. And what does that end up being?
1 over 10?
Is that 1/10? Yes, I believe you're correct. It's exactly 1/10. Interesting. All right. What is my AT and my AN? Well, what is AT? Well, there's two ways we could find AT. We could do the dot product version, or we could do the derivative of speed. By the way, it's always correct to do the dot and cross product versions. But what's my speed?
Constant.
Constant. So what's the derivative of speed?
0.
0. You basically just differentiated your speed there. Okay. And what's AN? Let's use the curvature one. So what's the definition of AN? Using the curvature one. The AN was speed squared times curvature. We could do the dot and cross product version, but this might be easier. So AN was the speed squared times curvature. I'll write it in that form. And again, whether you wrote it as dSdt or magnitude of v, you notice why I'm going to use magnitude of v, because I've already called something magnitude of v. So it goes back to your question is which one do we use? The answer is yes. Use whichever one at that moment in time makes more sense. I'm going to use this version because I've already got something called magnitude of v. I don't have anything that I actually specifically labeled dSdt, although that's what it is. So in this case, what would that be? It'd be 4√5 quantity squared times 1/10. And what does that end up being?
8.
Well, let's see, 4√5 squared would be 80, times 1/10 would be 8. So that means that you are telling me that A of pi is 0p plus 8n. And that's generally the way we would want to write it, as a linear combination of the t and the n. By the way, that's the best answer I can give. Remember, when we go outside, there's not a coordinate system. Oh, okay, so I'd say, the unit tangent is pointing that way, the unit norm is pointing that way. You're not going to have this. You're going to have things described as multiples of vectors now. Now, let's go back to here. This was our acceleration vector, wasn't it? Oh, here we go. What is 8 times this? Our acceleration vector. It's exactly what it says it's supposed to be. Now you guys can rejoice and, jump up and down and do the wave and all that stuff. I just picked this apart from sort of every point of view, but everything works together. The one thing you cannot afford is an arithmetic error early on, because it'll get carried through. But you notice how I checked my answer at the end of the problem? What if it didn't work? What if this didn't look like that? Well, then I know I've got an error somewhere, but that's a horrible place to find it, right, after I've just filled up a board. Now, what I just showed you is every conceivable question that we could possibly ask on this problem, and I did it all doing the direct main. So when people say, should I always use the backdoor methods? Well, no, use the backdoor if it looks like it's getting ugly quickly. How do you know when it's getting ugly? Actually, where is it? Sorry. Where's my T? Oh, that's my unit tangent. If that thing right there is not happy, well, what's not happy? Variables in the denominator. How often does that happen? Probably most of the time. Why? Because you multiplied by 1 over the magnitude, and magnitude is rarely constant. Okay, so it really depends on how gnarly is this guy. Does this guy have, square roots of t's in the bottom? If it does, then I probably want to go the back doors where I'm doing v dot a and v cross a. But this was sines and cosines. Doing the direct method was by far the fastest, just so you know. That's why I wanted to show you this. I have lots of examples of indirect. Question, on the other hand. Yeah.
So like this time the magnitude or the speed turned out to be a constant.
Because of the circular nature of the motion. That's unusual.
But like, what if it doesn't?
Oh, but then if it didn't turn out to be constant, then what it means is that this has a variable in it.
Yeah.
So this has denominators with variables. And that's most of the time.
Okay.
And by the way, it's still easy to this point. So when does it start getting nasty? Right about here. For those of you who've done some problems, you don't love that guy. Okay? That guy can be really, really difficult. If I have to find it, it can be really, really a mess. But that's why, because I said you're always doing these calculations at a particular value of v. So now when you find, or I should say value of t. So now you can find v of constant, a of constant. Now you're doing dot and cross products of those. And then this becomes really, really manageable.
So like the last derivative we need will be the acceleration, right? In that case.
Well, actually, in this case, this would be the last of the derivatives, probably.
Would we
And the reason I found the acceleration vector is so at the end of the problem I had something to compare it to. Because the point that we're doing is to write things in this form. Okay, that's the point of this problem. Because in reality, I said, all motion is circular, linear, or somewhere in between. The normal vector points to the center of the circle of curvature. So that means that all of this motion is circular. But three-dimensionally, that's why think of it as the corkscrew. What if this is not a zero? If that's not a zero, then this problem was probably way more challenging. And therefore, I would have probably gone to some of the backdoor methods. Okay? So I wanted to kind of summarize. If you look at the printed notes, I do several examples. And I chose functions that are not that messy. I chose functions that were not that messy. And for example, is it the second one? Where is it? Oh, on example 3. I'll use example 3 for example 3. On the tangential, I used a vector 2t, 2, 4t. Boy, that's about as friendly as it gets, right? I have t's and constants. But it doesn't take very long for you to see that, oh my gosh, this one here can get nasty really quickly. So I went right to the backdoor methods on that one. Because even though that was a really simple looking vector, it still can get really messy really fast. But the second example I did was this problem. And I'd use all the direct methods. The first example I did one that the numbers just work out really, really nicely. Things cancel really well. When you're doing the problem, how do you know which way to go? It really comes down to my unit tangent vector. If I have quotients of things. Now what often happens is, V might be kind of messy, but the magnitude of V, when I do, some of the messiness cancels out. I think the question Allison asked me was, on the quiz, I gave you stuff that you have to use product rule. You have e's and sines and cosines, and that looks scary at first. But you're going to be able to factor an e out of each term, and it'll probably cancel from the problem in the next step, which means all of a sudden, your unit tangent is probably really, really simple. And that's why you want to try it first. Find your unit tangent before you make your conclusion. If my unit tangent looks nasty, then I'm probably going backward. That's kind of the rule of thumb I think it's safe. All right? Now, let's move on now. And I promise you the level of difficulty of these problems, it will not be huge, because the point here is not to kill you on the calculus derivatives, magnitudes, because it can get so messy so fast. But like I said, if you are not efficient in your process, every semester I give the same problems, and I'll have people turning in short, sweet, and other people fill in pages because they left everything as functions of t until the very end and then evaluated, and it was too big. And the chances of getting a right answer when you have that much work, now your proofreading has to be otherworldly, doesn't it? So once you've taken your last derivative and all your answers are scalars, that's why I said, now go and evaluate everything. Please evaluate before you do your dot and cross products, so that you're doing them of vectors of scalars, not vectors of functions. It won't change your answer in the end, but it'll change the amount of work you have to perform. Okay, so we are now going to start talking about functions functions of multiple variables, and we want to talk about things like limits and continuity, some of the scary stuff. Now, we're not going to go into the epsilon delta thing, although that is part of the proofs that we do in 3D. So, a function of several variables. Most of the time, we're going to do functions of two variables. Okay, it's easier for us to conceptualize because 3 dimensions is primarily housed with functions of two variables. Your input and your output are x and y generally. So we're going to look at things of the form z equals f of x, y. So we're going to start with this basic notion, and we can describe a lot of things this way. And it's not complicated, but now for the first time, x and y are independent of each other. Now this is nothing like motion. We are finished with everything vectors for a very long time. Okay, at the end of the course, we come back to vectors. Now we're going to be talking about primarily surfaces. This is a 3-dimensional surface now. It's probably infinite, okay? A sphere, technically, we don't consider a surface. Do you consider a circle a function? No, but would you consider the top half and bottom half separate functions? Yes. So when I'm dealing with a sphere, we do spheres a lot because they're really happy things to work with. We rarely deal with the whole sphere. What we deal with is the top half or the bottom half, because those can be described as functions, just like a circle in 2 dimensions. So we say the surface might be the top half of the sphere. Does that make sense? Okay, so it has to be able to be described as a function before we do a lot of our stuff, because the derivative part can get kind of nasty. So with this, the first question is always domain. Now, if you think back to Calc 1, particularly if you're in my Calc 1 class, I said the first thing you do in every problem, before you do any calculus, is identify the domain. Think about doing an application problem. You want to maximize revenues or minimize costs and things like that. Well, whatever answer I get has to be within the realm of possibility. So we figured out, we make widgets and we charge a lot of money. We make a lot of money on widgets, and I did the calculus and I found to maximize my profit, produce an infinite number of widgets. Yes, that makes perfect sense, except that's probably not realistic. To minimize my costs, make a negative number of widgets. That's probably not realistic. Your answer needs to come from the domain of possible values. So every time you did anything in calculus, hopefully you looked at the domain first, because sometimes you had domains that were restricted. You would prefer in Calc 1 that all domains were all real numbers. Agreed? We prefer that. I don't like restrictions because I have to think about things that could go wrong. Well, in Calc 3, it's the same thing, but the way we express it's slightly different. So let me go back to Calc 1 for a moment. I've got f of x, let's keep it simple. F of x equals, let's say, the square root of 9 minus x squared. Okay? I want to know what is the domain of this. Now, generally speaking, when you answer a domain question, it's usually an interval that you give. You don't say the domain is x values because it wouldn't matter what letter of the alphabet I use. I could say f of t, f of q, f of p. It doesn't change the domain. The domain are the values I'm using, not the variable I'm using. So the easiest way to think of domain, you have a kid brother or sister who's doing algebra for the first time and they're asking you, what does domain mean? What sort of words would you use? There's one word I like to use. All the possible inputs. What can I put in? See, when you're thinking a range, what are you thinking of? All the possible outputs. And by the way, it's an almost never, in any conceivable context of mathematics, do we even care about the range, believe it or not. Because almost 100% of the time, you can't even talk about the range if you don't have a graph of it. But the domain, you can always figure out without the benefit of a graph. What can I legally input? And in calculus, for Calc 1, 2, and 3, we do what are called real-valued functions. And I don't say this jokingly. We don't deal with domains that involve complex numbers in general. Not yet. That is coming, just not yet. So real-valued functions means all my inputs have to be real and all my outputs have to be real. Okay. See, if I said x is all real numbers, there are a lot of outputs that will produce imaginary numbers, won't they? And then that's no longer a real-valued function. So I've left the realm of possible answers that I can give. So I only want the inputs that keep the outputs real. That's what it means. And we would all do that automatically, but there are functions out there that there really are no restrictions as long as if I allow complex or purely imaginary numbers. So sometimes we forget that, but that's actually there. See, I can take the cosine of an imaginary number. There's nothing wrong with that. But if I take the cosine of an imaginary angle, I just get back a real number outside of the range of -1 to 1. So if there are no restrictions on the cosine, then the range of values for cosine is actually all real numbers. But most of those come from imaginary inputs. That's what the hyperbolics tell us. So we don't want to go there. That's a whole other thing. That's upper division stuff. So I need to do a little bit of algebra to figure out what I can use. So what sort of restriction am I going to place on this?
Greater than or equal to 0.
Greater than or equal. Equals okay. Less than bad. So if I do that, then that means that x squared is less than or equal to 9. Then that means the absolute value of x is less than or equal to 3. Do you all agree with that? I'm being lazy here, right? That's simple. So as an interval, that's not an answer, but that was my simple algebra. As an interval, what would that be? All right, think number line, that helps. So I'd say, all right, I am the interval from -3 to 3, open or closed? Can I have the endpoints or not? Yes. So do we all agree that that would be the domain? And that's the way we would say it. Now, let me tweak this. Does anything change here?
You can't have the endpoint.
Now I would change it from closed to open because I can't equal 0 anymore, can I? Okay, that was a simple tweak. That's how we would answer it in a calculus class. Now I want you to go back to baby algebra. And the funny thing is the algebra books, they'll ask for domain and they'll give you answers that aren't intervals. And it never makes sense to me. They use what's called set builder notation. And so here's what an algebra book would say for the same problem. They'll say the domain is the set of all numbers x such that x squared is less than or equal to 9. And that's a correct answer, by the way. But have they told you what the domain is, or do you still have to figure it out? Or if they're really useful and they're on top of it, they might say such that x is between -3 and 3. Now, all of a sudden, that was way more useful. But we know in a calculus sense, we always give answers as intervals. This is called set builder notation. There's nothing wrong with it, it's just not particularly useful until now. Because we're going to talk about domains in 3 dimensions. You cannot give an interval in 3 dimensions. You can only give an interval on a number line. Oh, so now our domains are not intervals, our domains are ordered pairs. What ordered pairs can I input? And it turns out set builder notation is really the only way I can express that answer. So that's why I'm reminding you of something you may have done in a remedial course, which you didn't like because it seemed like you're not finished. Right? It does feel like you're not really finished. Set, the notation is actually quite important. This is the set of all x's. Technically, no, it's the set of all real numbers. The default is real numbers. Some textbooks will say the set of all x in the set of real numbers such that. That is correct. If this was discrete mathematics, has anyone have Math 245 yet? In discrete mathematics, you almost never use the real numbers. That's not discrete, that's continuous. Oh, so if this was discrete mathematics, I'm probably only using integers and at most rational numbers as my input. But I'm not using real numbers as my input because that makes it continuous and not discrete anymore. In case you're wondering what's the difference. How many children do you have? That would be a discrete calculation. How old are you? Right? How tall are you? How fast can you run? What time is it? Those are continuous calculations, right? Those are infinite decimals and so on. Right? How many lengths are there between 1 foot and 2 foot? Infinitely many. How many children can you have between 1 and 2? There are no values. Discrete versus continuous. So I think of discrete as counting. Continuous as measuring. So this is correct. In another class, it might be a different thing. It might be integers. It might be, like I said, rational numbers. But in a higher level class, it might come from the set of complex numbers. The default we generally work with when using set builder notation, it's automatically from the set of real numbers. Therefore, you do not have to say this. That's kind of the default. That's already there, so you're kind of off the hook. So here's my function now. My function in 3D, let's keep this really simple. So my input now is ordered pairs. So I have a similar restriction than we just had a moment ago. Okay? I have a similar restriction that we just had a moment ago that I have to be, non-negative. So would we start by saying x squared minus y squared must be greater than or equal to 0? Do you all agree with that? It's a good starting point. So x squared must be greater than or equal to y squared. Can either x or y be negative?
Depends what the other one is.
Well, can they be negative?
Yes.
If x is negative 10 and y is negative 5, is there any issue there? What if x is negative 10 and y is positive 5? Is there any issue there? What if x is negative 5 and y is positive 10? It's the squares. Oh, okay. There are values that I can't use, clearly. Boy, is there an easy way to say this, maybe?
X is greater than or equal to y. Absolute value.
Yeah, probably want to go with absolute values in this case, because of the squares part. By the way, what you said is correct, but I might have to do all the cases. So, would this statement here be correct? Stare at that for a moment. As long as the absolute value of x is bigger than the absolute value of y, then the square of x will always be bigger than the square of y, and they could in fact be equal. That would be okay. So is that okay? Some of you are shaking, some of you are nodding. Yeah, this is actually okay. Because you just said x could be negative, and as long as x is a bigger negative than y is negative, x lost more money than y lost. Okay, that's okay. Now, here's a suggestion I always make in this sense. Draw a picture. Not of the function, but of the domain. Sometimes it helps you understand what you're saying if you actually do a picture. Now, if I think of this just for a moment as an equal sign, y equals x would be this line right here, correct? Y equals negative x would be this line right here. So I want the relative size of x to be bigger than the relative size of y. Where am I going to be then? The easiest way to do is just make up a quarter. Okay, 10 comma 5. Let's see, 10 comma 5 would be over here. I'm pretty sure that will work. How about 10 and negative 5? So all of this is in my domain. 0 comma 10. That won't work. Do you agree? 0 comma negative 10. That's not going to work. None of that, none of that. All right, how about negative 10 comma 5? Will that work? Yeah. How about negative 10, negative 5? Yeah. Okay. So my domain is half of the xy plane. Do you agree? Now, there's really no clean, simple way to describe that, but sometimes there is. Sometimes when you're doing the problem, you'll say, oh my gosh, my answer is just the second quadrant, or my answer is just, above the x-axis, whatever, because you did it. Now, there's no easy way to describe this as like one term. I like that. That's okay. I think that would probably be easier than to try to make it, if I take off the absolute value, I got to do too many conditions, I think. So, how do I answer the domain? The set of all ordered pairs. That means the set of all coordinates in R2. That would also be correct. But you don't need to say element of R2. That's implied. It's an ordered pair. Such that the absolute value of x is greater than or equal to the absolute value of y. That's it. That's all I need to say. That's good enough. Okay? Let's do one more that has some conditions, because the conditions sometimes give us trouble. about, let's say, f of xy equals the square root of x plus y over the natural log of x. This is the one that gives us the most trouble in terms of how to state the answer, even though it doesn't have to. Okay? Now, back up a little bit to baby algebra. I mean, baby algebra, not calculus. If I was to draw this on a number line, you'd say, I want to be greater than 3 and more negative than -6. Would you agree with that picture? When I taught algebra, I always tell, draw a picture first. Now, the answer to this question should be interval notation. But if you draw the correct picture, sometimes it makes the interval so much easier to state. Can you write this as one interval? Is it possible to write this as one interval? No, there's two intervals. So what would I write? I'd write -infinity to -6 union 3 to infinity. That would be the correct way of writing it. Okay? So far, so good? What if I have something like this? X is greater than or equal to -2, and x is smaller than 5. There's something that I want to make sure everybody remembers, because you've all learned this at some point in your life. So there's -2, there's 5. I want to be greater than -2 and smaller than 5. How do I do that? Where am I shading? This is what we call a tweener. Oh, I want this. See, greater than -2 is this way forever. Agreed? Less than 5 is this way forever. And the word and always means intersection. Oh, so this would be then -2 to 5. The word or always means union. You're in this or you're in this. You don't have to be in both. Okay? Or always means union and always means intersection. So when I'm using words and I'm talking about intervals, or and are huge. If you had said and instead of or, what would the answer to this be? What's in my domain?
-6 would be.
Nothing. It'd be the empty set. Oh, are there any real numbers that are simultaneously bigger than 3 and smaller than -6 at the same time? No, that'd be impossible. Oh, so or versus and is actually quite important. We want to get the language correct because it's not interchangeable. Does anyone here ever write computer code? Are ors and ands kind of important? Or, and not are probably the three most important because it does matter. See, I always talk about, when I'm teaching this, especially when I'm doing logic, which might be in discrete math, maybe in statistics, different areas where you're doing counts. So, okay, I just recently went on a job interview. And like any good job interview, I'm sitting there and I got the long table of, scary looking people, and I basically am conducting the interview as to whether they're worthy of my skills. So before the questions started, I said, I have a list of demands. Okay, I want the 7-figure salary. I want my own parking space. Keys to the executive washroom and the letter M stricken from all company language. And they get together and they talk about it and they say, well, we can do everything except the parking space because, it's kind of limited. Will I accept the job? You have to be paying attention to what I said. Why not, Samuel?
Because you said and.
Because I connected them with an and means all things have to be true or it is not true, which means when you have multiple things, the intersection gets smaller. When you connect things with the word and, all of them have to be true simultaneously. So we say the word and is very exclusive. If any part of the and is not true, then the whole thing is not true. So I come back with my tail between my legs for a second interview next week, and I say, okay, I've changed my demands to 7-figure salary, or parking space, or keys to the executive washroom, or the letter M thing, and they come back and they say, we can do keys to the executive washroom. Am I going to take the job this time? Yes, because I connected them with the word or. If any part of an or is true, then or is true. All parts do not have to be true. If any part, or is very inclusive. If any part of a union is true, then the whole union is true. Does everybody understand? There's a huge, so anybody who's ever written computer code, you have an understanding of this, how ridiculously extreme those are, but it's just a word. Yeah, but it's also what the logic is based on. So when I'm writing this, think of this as two completely separate problems to start. I have the numerator, I have the denominator, let's treat them separately. Okay? So what's important in my numerator? Do you agree that x plus y must be greater than or equal to 0? Equal 0 is okay. And how about my denominator?
X does not
Can't be
equal 1.
zero.
X has to be
Greater.
greater than 0
And
and not equal to 1. Oh. X is greater than 0 and x is not equal to 1. By the way, what am I putting between these things? Or and? I'm coming up with the domain of a function, and I have multiple restrictions, clearly. All restrictions have to be satisfied at the same time. There has to be an and. There's a flippancy sometimes when we're doing this, we just kind of take it for granted and we connect everything with the word or because it doesn't really matter. Well, actually, it really does matter. Okay? So I need this to be true, and this to be true, and this to be true. Oi. Okay? I don't feel very clever today. Can I just go with that? I don't really need to whittle it down. Nothing's going to cancel. So when I'm writing this, by the way, if you wanted to say x is greater than or equal to negative y, that's okay. There's nothing wrong with that. Or if you wanted to write what y is, you don't have to be clever. But the point is how I finish this is the key. X plus y is greater than or equal to 0, x is greater than 0, x is not equal to 1. What do you think of that answer? You should be. In baby algebra. Correct? Is this what we'd all write in baby algebra? What else would we write in baby algebra? You might say, I usually start with that. Absolutely in a mathematical context, what does this mean? Or. It always means or. Because can x equal 3 and at the same time x equal negative 3? That doesn't make any sense whatsoever. Oh, I have a whole list of things, a whole list of people that I want to invite. I'm going to invite you, or you, or you, or you. Or I can say and. But when I'm talking about numbers, this means or. Oh, so I just said if this is true, or this is true, or if any of these conditions is true, I'm good. Then I'm going to have a lot of problems, aren't I? That's what I'm trying to show you. Now I have to connect these with an and. That's where we get in a little bit of trouble. By the way, I don't think people are going to think you're bad at math or something because you used a comma, but it's very possible it's going to be misinterpreted. Because when I see possible solutions to a problem, they're always connected with commas. Because they couldn't be simultaneously true. X can't take on multiple values at the same time, but it can be this or this or this. And like we just said, we know this from inequalities. When I'm doing inequalities and I have an and versus an or means I'm probably shading most of the xy plane, and and means I'm only shading a little bit of it. So which one I do is actually important. Minor thing, I just want you to get that. This is a fairly simple notion. Now, the next thing I want to talk about is the slices. Okay? I'm going to give you a simple illustration. This is a map. And let's say we're looking at maybe like Borrego Springs or something. Anybody ever been to Borrego? huge desert. It's really flat for a lot of it, but there's hills and things out. So I'm looking at this map, and here's what I see. This isn't necessarily Borrego, by the way. There's some. So let's say that the outer circle means 1,000, and then the next one is 2,000. This is elevation, and that's 3,000, and so on. So 1,000, 2, 3, that's 4,000, 1,000, that's 2,000. I'm looking at a map. Could you loosely construct a three-dimensional map right now of what I just did? Yeah, you say, okay, this is going to go like that, and this one's going to go really high, it's going to be 4,000 feet high. Has anyone ever seen a map look like this? What is this called? A topographical map. It's a two-dimensional rendering of a three-dimensional region, and none of us have any difficulty interpreting if we know that's what it means. Oh, each of these rings, it would be as if I have a hill that's 4,000 feet high, and I sliced it at 3,000 feet, and what did I see? I saw this outer edge. And then I took 2,000 feet, and I sliced it every place where it's exactly 2,000 feet. I sliced it horizontally. Okay? That's what we're going to do with functions. We're going to slice them. Okay? And when I slice them, that's called a level curve. I think I've used this term once before. Yeah, exactly.
If you have like a shape that goes up and then dips, how would you represent that in?
I think that might be kind of difficult, so yeah. I'm trying to keep something simple. Yeah, you have to ask the tough questions, don't you? So a level curve would be a slice of a three-dimensional shape. So let me start with something that we've actually done before, so a little bit of familiarity with this. Let's consider I have f of xy equals x squared plus y squared. Okay? So that's z, by the way. Z equals x squared plus y squared. That's automatic. In Calc 1 and 2, when you wrote f of x equals something, didn't you automatically interpret f of x as y? Yeah, I mean, you could use different variables, but it's convenient to use x and y. Right? We get comfortable that way. It doesn't have to be, but it just makes a lot more sense if we're consistent. So that on the left is z. All right? I want you to find, we want to find the level curve at, how about 2, 4? That means my input is 2, 4. That means I'm literally looking at my topographical map at the coordinate. See, this is a two-dimensional graph, isn't it? So what is f of 2, 4? There's, put the numbers in. What's f of 2, 4?
20.
Oh, I'm sorry. Did you say 20? It's the mask. Sorry. I thought you said something else. All right. So what does that mean? Well, in terms of an illustration, this we know is a circular paraboloid, and if it helps you, since that's z equals, cross sections in the xy plane are circles, cross sections in the xz and yz are parabolas. It's a circular parabola. I mean, we just did stuff like this recently. I asked you to do a certain input, 2, 4, and that took you, let's say, to about here, let's say. So that point is 2, 4, 20. Does that make sense to everybody? Where that just came from? So what I've got now I have very specifically, okay, that's supposed to represent a circle. I have very specifically a circle. What circle do I have? X squared plus y squared equals 20. If I'm standing on top of the z-axis and I'm looking down, and close one eye, so now you're seeing two dimensionals, this is the circle you're going to see, isn't it? So it's a two-dimensional shape because I just took a slice, 20 units off the ground, if you will. That's called a level curve. And I'm going to show you guys that this is kind of one of the coolest things. Everything you've ever done in your entire life in 2 dimensions is a level curve of something in 3. There's no exception. There's nothing you can come out with that didn't come from 3D. Everything in 2 dimensions is a level curve. of something in 3D. And one of the reasons that's so cool and powerful is things that aren't necessarily functions in 2 are usually functions in 3. You see, we know a circle is not a function in 2 dimensions, but this is most definitely a function in 3. And so things like the calculus of this is much easier if I actually look at it as a 3-dimensional thing rather than a 2-dimensional thing.
So can we extrapolate that things in 3D that are not functions, like a sphere?
Yes,
Are they
but they
functions
could
in
be,
point?
yeah, hold that thought because we're going to actually just look at that. We're not going to spend a lot of time in higher dimensions. We're just not. If you're a math person, and I mean you want to study mathematics, maybe you want to get a degree in mathematics and you want to go into the abstract realms and there's crazy cool stuff. But Calc 3 is supposed to be about the most applied math class you will have ever had in your life. So we tend to stay away from the abstraction in this class. But I point out that we're right on the edge. And then you could take an upper division version of a math class that now deals with the abstract parts. So yes, higher dimensions are there and they're very important to study. We don't need them for what we're doing now. And it's funny that you asked that. I talked to some of you last week after class, and I was mentioning a book that I read several summers ago called YE=mc². And some of you heard that conversation, and it's written by 2 Cambridge physicists. And it starts off with them saying, you don't have to be a math or physics person to understand this book. We're going to use really simple layman's terms. So after reading this, I found out if I run really fast, I will age slower than you. That's one. And on a train, you have like a pendulum clock on a train, you can actually prove very simply that time really does slow down. You can actually physically see it. But the most important thing was, to prove everything they did, they used what's called non-Euclidean 4-dimensional vector geometry. I have multiple degrees in mathematics, and I barely understood what they were talking about. And they said you don't have to have any background in math or science. I kind of disagreed after about the 2nd or 3rd chapter. I think you had to have a PhD in both. Yeah, it was really complicated really quickly, but I just thought it was funny. These guys must be on such a higher level of thinking that they wouldn't think you needed any math or science to understand their non-Euclidean geometry is hard enough. Non-Euclidean 4th dimensional geometry is really, really difficult to comprehend because we live in 3. And that's what the whole thing, all the theory of relativity is based on. I have fun with that because I understood some of the geometry because I've done that. But I'm guessing the average reader, even with a math background, would not have understood it because they didn't do that. Not everybody does the same courses when you're doing math. You choose very specific routes, okay? Like you have different degrees of engineering, right? They're not all the same thing. So a level curve is a slice of a 3-dimensional thing, a 3-dimensional function. That's it. There's nothing about it that's complicated. But what we're going to do is use this to our advantage later to do things like different types of derivatives. So if I have something in 2 dimensions, I can always work backwards and say it came from something in 3D. How would I do that? Well, I'm going to prove to you that everything 2-dimensional, everything, is a slice of something in 3D. Okay? Y=f of x. Let's start with a function just to make it easier. Okay? So far, so good? F of x has xy things, right? I have x's on the right side. I don't have y's on the right side. I have a y on the left side, I have x's on the right side. There. I've just created a 3-dimensional function. Then how do I get this? Well, take the level curve when this equals 0. This is actually the proof. I just proved that every function in 2 dimensions is a slice of something in 3. What? Yeah, it's actually that simple. But then I could have lots of slices. I could pick all sorts of different values for this, and then it would give me different functions. Well, yeah, that's the kind of stuff we're going to do. It's clever math to get our goals accomplished. So Zachary asked the question about higher dimensions. And this is actually almost as important, although we won't use it quite as much. Okay, I mentioned to you guys last week that temperature is technically 5-dimensional because there are 4 inputs, right? The X, Y, Z, and what was the 4th one, remember? Time. At different times of day, at the same place on planet Earth, different times of day, I'm still going to have different temperatures. Let's keep it simple. Let's just take the time out for a moment. Let's just say X, Y, Z. Okay? So I'm going to have a function I'm going to describe a really simple function. Okay? This is a function of 3 variables, so this is a 4-dimensional problem. Pick any positive value, or you could make it even easier. Pick any real numbers for x, y, and z. That might be easier. So let's say I'm interested in f of -1, 2, 4. Okay. What's f of -1, 2, 4? That'd be 1 plus 4 plus 16, or 21. Agreed? So what if I now considered the following? I consider x squared plus y squared plus z squared equals 21. Slice may not be the right word, but it's kind of a slice of this, isn't it, for that input. But this is now a 3-dimensional shape that came from a slice, if you want to call it that. Not really a slice, but of that thing. This is not a level curve. This is a level surface. For the same idea, I have one more variable here. So this thing here, at first glance, you want to say sphere, don't you? At first glance. But the problem is that for every value of x, y, and z, I'm going to get a different input that's on a different sphere. Oh, so I just picked a particular x, y, z that gives me one very specific sphere. Another way of thinking about it would be, there's the origin. Let's take any point in the room. We're in the first octave. Let's take any point in the room. How would you find the distance? When you say x squared plus y squared plus z squared and then take the square root? What if we just left it as x squared plus y squared plus z squared and just called it the square of the distance? Leave out the square root for a moment. Then every point in the room would have a different sum of squares. Do you agree? But aren't there points in the room that have exactly the same sum of squares as this point? Yeah, and all of them would live on the same sphere. Oh, because the x squared plus y squared plus z squared that gave me this value? If I use a different x, y, and z that gives me the same value, that means because they're on the same sphere. Oh, so what I have technically then is an infinite number of spheres that are all concentric. That's kind of cool, isn't it? That's what this would be in 4 dimensions. It'd be an infinite number of spheres. Because for every positive number I have on the left, I would have a different sphere. Could I technically have negatives on the left? How could I have a negative on the left? Only if I allowed imaginary input on the right. And since we're not allowing imaginary input on the right, there is no negatives on the left. Does that make sense? If we allowed imaginary input, a whole can of worms is opened up. That's not something we explore. I don't need you to think of what this looks like in 3D. It's 4-dimensional. But for every ordered triple I give you, there will be one very specific sphere that passes through that ordered triple. That's the way you can think of this. For the ordered triple in 3 space, -1, 2, 4, this is the sphere that passes through that point. Give me a different ordered triple, there'll be a different sphere. So this is called a level surface. The other one was called a level curve. We don't need to go any higher. We don't spend a lot of time with this, but just to be aware that it's there. Remember last week when I blew some of your minds when I talked about shadows? Remember that? What are you the shadow of? That's exactly the mathematics right there. That sphere, this sphere is a shadow of this, if you will. It's not a projection. No, projection means that I'm still in the same dimension. Whoa, I got kind of crazy. Now the last piece of the puzzle we need to talk about today, none of this, by the way, should challenge you. This is actually arithmetic for the most part. If I say, here's a point, give me the level curve, it's actually, this is what the answer looks like. And you say, okay, it's a circle of radius root 20, something like that. Limits. Limits are where it gets a little bit tricky, and we need to review limits. We're only going to spend a very short time. Okay, Calc 1, you spend a lot of time on limits because the development of almost every calculus formula involved limits. In Calc 2, you looked at different types of indeterminate forms, particularly those that required L'Hopital's rule. So you now basically can take every limit that exists in 2 dimensions. And I have bad news for you. You're never going to use L'Hopital's rule again the rest of your life. I looked. I made sure. Yeah, to be honest, after the middle of Calc 2, you never actually use it again in any math class you will ever take the rest of your life. Why? Because it only works when there's one independent variable. You're working now in 3D. It doesn't even mean anything. And then in other classes, it's higher dimensions. It's a cool thing to use when it's relevant, and it's, yeah. People say, can't I use L'Hopital in Calc 3? And I always tell them the same thing. Look, if you could figure out a way to prove a way of doing L'Hopitals in Calc 3, that'd be awesome. It'd be a guaranteed PhD, but I guarantee for the last 300 years, people have been trying to do that. No one's come up with it yet. You're good, but if in 300 years no one's come up with it, I'm guessing maybe we won't either. So, yeah, unfortunately, it won't work for our limits because we have multiple variables. But we still need to be able to take limits because we're going to define the derivative next day. And the derivative still has to be based on a limit. So I got to be able to take limits. So let me go backwards in time and remind us of what we already knew from Calc 1. Because we're going to use the exact same algebra. We're not going to change the way we do things. It's just going to be more variables. So in Calc 1, we had a problem. Let's say this was the problem. X goes to 3 of 2x squared minus 4x, say minus 6 over x squared minus 9. I have something like this, okay? Now, the rule of thumb is always, can you evaluate that function at 3? If you can, do it and move on. But if evaluating at 3 produces an indeterminate form, of which there are many, in Calc 1 we mostly looked at 0 over 0, infinity over infinity. Those were the two that we typically dwelt on. So what you did was you said, well, what is the form? I can't evaluate this if I get a 0 in the denominator. So what do I get on top? Get 2 times 9 minus 12 minus 6, that's a 0. And I get, no, that's a, oh. So we'd say this is the indeterminate form. It does not equal 0 over 0, because 0 over 0 is not a number. You can't equal something that's not a number. This is the form. So think back to Calc 1. The form dictated the strategy, didn't it? Oh, because the form infinity over infinity, now I looked at things like degrees. 0 over 0, I probably wanted to do a factor and cancel. What if it's something not 0 over 0? Oh, now it's the asymptotic. Ooh, those are the ones we hated the most. Right? There's different forms that it can take on. This means factor and cancel. Okay? So I don't have to be a rocket scientist. I can do this one. Now, from the fundamental theorem of algebra, this is one of the most important things you ever learned in your life, pre-calculus. If a polynomial equals 0 at any value, then x minus that value has to be a factor. So that means x minus 3 has to be a factor of the numerator, since the numerator evaluated at 3 is 0. Boy, does that make my life easier? Yeah, I don't even have to be good at factoring. That's an absolute. Oh, okay, let's see. I'm going to put a 2x here, and I think a plus 2 over here. Quick check. Okay, boom. Okay, perfect. Sometimes we forget the obvious. Remember, if a polynomial, here's the easiest way of saying it. For a polynomial function, if f of c equals 0, then x minus c is a factor. That's part of the fundamental theorem of algebra. That's how you did stuff in pre-calc, rational root theorems, factoring higher degree things. So in this case, can I do this? Is that legal? Is that legal? And we sometimes forget the why. So I want to remind you of the why. Has anyone here tutored calculus? You've tutored calculus? You get why a lot?
Yeah.
A lot of folks, unfortunately, people want to, okay, here, just tell me the answer. No, you don't want the answer. Right? You want to know the why so you can answer the next question. And it actually is corny, but it's like the old expression, was it give a man a fish, he eats for a day? Teach a man a fish, he eats for a lifetime. You tell them the answer, they got that problem, they can't do anything else. You tell them the why, they can do everything else. And so we sometimes forget. I'm in a baby algebra class. I'm in baby algebra. I taught remedial algebra for years and years and years, and so you'd be told to simplify the quantity. That means you're going to factor and cancel, obviously. What is the domain of this? All you have to do is look at the bottom. Would you say all reals, let's be really lazy, except, would you say all reals, I'll just in English, all reals except -3 and 3? Do we all agree with that? Now, you just did some algebra and you found that this reduced to this. We just did it. At first glance, what does it appear the domain of this guy is? All reals except -3. Is there anything wrong with that statement?
The absolute value.
No, it's not that complicated. What's wrong with that statement, Zachary?
It's still the same function, it's just.
Yeah. There's an absolute mathematically, a domain cannot change. Period. A domain cannot change. The domain of this function was all reals except these two numbers. It's still all reals except those two numbers. But it has the appearance that it's different. So in remedial algebra, I had them right. By the way, what did we just cancel? We canceled the x minus 3. So it almost seemed like we removed 3 as a problem child. So what do? We said it's equal to this as long as x is not equal to 3. We removed that discontinuity from the problem. That's why x equals 3 is called a removable discontinuity. Remember that term? Oh yeah, in fact, I apparently removed it from the problem. No, you didn't, it's still there. But here's the beauty. A limit is not a functional value. A limit is where am I headed? As I approach a value, where would I get if I could actually get there? But there's a hole. If I did a graph here, we know there's a hole where x equals 3 is. There's nothing there. It's not 3 is not in the domain. There is no functional value there. But if there's a hole there, where is the hole? What is the ordered pair that produced that hole? That's what we did in Calc 1. Oh, okay. The limit as x approaches 3 is not what's happening at 3. It's happening as I approach 3. I never actually get to 3. Right? Limit means you approach, you never reach it, but where would I be heading if I could get there? Can I evaluate this at 3? I get 8 over 6 or 4/3. Do you agree? Does that mean the functional value is 4/3? No, there is no functional value. But it means if I were to produce a graph of this, there is a hole. There is a hole at 3, 4/3. Now, when you're in Calc 1, you don't always see that. That's not always clear. You're just hanging on for dear life, hoping you can get the right answer. But in Calc 3, you look back and go, oh, that's what I was saying. I have a discontinuity, but it's literally 1 point removed from the graph. That's why if I did this on a graphing calculator, it would appear that it's continuous through that, because I only removed the point. So I'm not saying what the functional value is. I'm saying if I could get to the hole, where would the hole be? And that's where the hole is. That's why that's the limit. I don't have to put a disclaimer on this, because the limit as x approaches 3 is saying what happens as I get close to 3, I never get to 3. The domain is still, 3 is not in it, but I can say as I get closer and closer to an x value of 3, the y value is closing in on 4/3. That's why that's the limit. So the factor and cancel was a real common one that we did. The one that we didn't like, there was a lot of ones we might not have loved, but one like this. Okay, this is what's called a piecewise function. We rarely ever dealt with these. We do a little bit of this in differential equations for different reasons. We rarely dealt with these in calculus because they're not really convenient, but they are to illustrate the following. So if I asked you, because we're going to do a version of this in 3D in a moment, if I asked you then, what's the limit as x approaches any number, would you say it's an easy question in general? Yeah. In fact, I'll draw a picture of this graph. Right? This graph looks like give me any x value, and this is a piece of cake, as long as that x value is not what? 0. So of course that's the only one we're interested in, because everything else is just boring. The previous question, if I had used a different x value, that would have been boring. So how did you do this in Calc 1? Do you remember, Zachary? What do you think?
Specify what direction you're approaching from.
Yeah, so this is the only time you had to consider directions. A lot of folks say, well, do I have to do the left and the right in every limit? No. You only do the left and right if you think it might be different. In the last problem, I didn't consider one-sided limits because that wasn't an issue, but this is a piecewise function. This is a different function to the left and to the right. So what you did here was you took the limit from the left and showed that that limit was 0. You took the limit from the right, showed that limit was 1, and you said along 2 different paths, I got 2 different values. Therefore, what's the answer? D and E. You didn't like those. You always thought you did them wrong, but that's the correct answer. Now, does the limit from the left or the limit from the right exist? Yes. As a rule of mathematics, the one-sided limit always exists as long as it's within the domain. I have to throw that disclaimer because there's even exceptions to that. A one-sided limit is pretty much always going to exist. Here's what I mean by within the domain. If I said, what's the limit as x goes to 0 from the right of square root of x, you'd say that's 0, piece of cake. What's the limit as x goes to 0 from the left of square root of x? What do you think?
D and E.
D and E because there's nothing to the left. The domain starts at 0 and goes to the right. Oh, coming from the left of 0 means I'm coming from outside the domain. This is the only time a one-sided limit won't exist, because I'm actually outside the domain. But this one-sided limit was fine. That's why the trick question that you always get in Calc 1 is, therefore, what is the limit as x approaches 0 of root x? Well, don't most people say the answer is 0? But what is the answer? D and E because the limit from the left didn't exist. Oh, okay. Remember, for limit to exist, it has to exist from both directions. In Calc 1 and 2, we have one independent variable, so there's only 2 directions I can ever approach a value from. Agreed? Guess what we're going to be doing? Our domain is now on the xy plane, not on the x-axis. It's on the xy plane. So maybe there's a point, 1, 2 that I want to approach. From how many different directions on the floor can I approach 1, 2?
Infinite?
Infinitely many. But if I was on the number line, how many ways could I approach the number 1?
2.
Only 2. Oh, so this definitely throws a monkey wrench in here, doesn't it? On the xy plane, there are an infinite number of directions you can approach a point from. But on a number line, there's only 2 directions you can approach a value on because you're one-dimensional. So when I'm doing a similar problem, like a D and E kind of problem, what I do is I try to show, and we're going to do an example of this in a moment. I try to show that at least 2 different paths produce different limits. I don't have to prove an infinite number of different limits. No, 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 no. I don't have to prove that every conceivable path, of which there be infinitely many, will all produce different limits. No, 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 no. I just have to show that if I approach it from more than one path and I get more than one limit, that's good enough, just like this one. But that one's a bit trickier, so we're going to go over that one in a moment. Not yet. All right, so let's do what I would consider a fairly simple one. One that kind of looks Calc 1-ish. All right? Let's see. Let me start with something simple. Give me 1 second. I like to. Okay. So I want to do the limit as xy approaches -4, 3 of 3x squared minus 2xy minus 8y squared over x squared minus 4y squared. Did I do that one correctly? Oh, no, I'm sorry. No. What was I thinking? Sorry. 9x squared minus 16y squared. There we go. All right, can everybody see what I have just some function. There's nothing special about it. In fact, it's a rational function, which makes life a little bit easier. If I just grabbed a random ordered pair from anywhere on planet Earth, I can probably evaluate this. Now, let's go backwards a little bit. What is the domain of this function? When you have a quotient, the restrictions can only come from where? The denominator. If I have a logarithm, they're going to come from the argument. If I have a square root, they're going to come from the argument. But in quotient, I don't care about the numerator. I only care about the denominator. So tell me about what restrictions do I have? 9x squared minus 16y squared cannot be what? 0. That's it. Oh. That is my only restriction, that that cannot be 0. So, let's see, that would mean that 16y squared cannot be 9x squared. So that y squared cannot be 9/16 x squared. So how about y cannot be plus or minus 3/4 x? I'm going to be really lazy. All right, so look at your xy plane. Remember, this is a surface. This is something above us. Okay, the way I like to explain surfaces in general, and I use this analogy all throughout the course. Right, you're making your bed. You ever do this? I do, especially when my kids were little. They used to like darting underneath. I fluff the sheets, and if you get it perfect, then what do? You just let it drop, right? And it's perfect. Anybody do that? I do this when my kids were little, and it's like fluff, like the torpedo dives in the bed. You know, it's kind of fun. But I fluff the sheets. So here's what we're doing. I'm fluffing the sheets, and then you freeze frame. And what do you see? Rolling hills and valleys of the sheet. That's the easiest way for you to conceptualize any surface. It's just rolls and it's just the sheet. You know, it's not a plane. It's got hills and valleys, and it's all independent, and it goes forever, perhaps. But it's above the xy plane, which is where the input's coming from. The line y equals 3/4 x is going to cut through this way forever. The line y equals negative 3/4 x is going to cut on the other side that way forever. So in a sense, my domain is all ordered pairs on the xy plane except for the ones on those two lines. So what does that do to a three-dimensional shape? Instead of a hole, it creates kind of a fault line in a sense. It's kind of cool, isn't it? So there's like an infinite fault line that points cannot come from. Not a hole, anything on the line. Okay? So anything on these two fault lines I cannot do. Well, where does negative 4 or 3 live? What lives on that fault line? Okay, so clearly there's a problem there. So if I try to plug in negative 4, 3 into the numerator, what will I get? Anybody try it? Hopefully I do this right. If I put in a negative 4, 3, then I'd have 3 times 16 plus 8 times 3 minus 8 times 9. So that's 48 plus 24 minus 72. Oh yes. That is very much 0 over 0. So what does that mean? That means on my surface, I have one point. On my surface, that's going to be removed. Any suggestions on how I might want to approach this? It is a rational function.
Factor and cancel.
Factor and cancel. If I had square roots, sometimes we conjugate, right? If I have trig stuff, it can get really icky, but factor and cancel will still work. I made this particularly not horrible, all right? Well, the problem child is negative 4, 3, so perhaps this is going to factor very nicely. How about on the bottom I do 3x plus 4y times 3x minus 4y. Now, which of these two is the problem child? The first one or the second one? Where is the 0 coming from?
The right one.
It would be this one, wouldn't it? So if I do 3 times negative 4 plus 4 times 3, see this one's not a problem, it's that one's the problem. So what does that mean? You got one of these on top too. So what do I get? Yeah, it actually is this easy to factor once I determine that. So they give me x minus 2y, quick check. That would be 4xy minus 6, okay, and then, okay, good. Is this a good thing? Yeah, this is a great thing because I can now cancel. I am removing one of those fault lines from the problem. When I cancel this, I have removed one of those two lines now as being a problem, apparently. So in a sense, like a removable discontinuity, except it's a whole line of discontinuities. Now, one of the great things about doing a limit is you don't ever have to put the disclaimer. You see, x and y are never going to get to this. They're only going to approach this. So I don't need to say, well, these are equal to this as long as x comma y is never equal to this. It doesn't, I don't need to do that because I'm never actually going to get there, am I? I'm just going to close in on it. So what's left? I have x minus 2y over 3x minus 4y. Is there any weirdity going on here at this point? Nope. So therefore, now I can evaluate. I want to remind people that when you evaluate the limit, you don't write the word limit anymore. There's two common errors that we make in Calc 1, and I'll show you what they are in a moment. So if I put negative 4 comma 3, that'd be negative 4 minus 6, that's negative 10. Negative 12 minus 12, that's negative 24, so what, 5/12. Okay. This is a perfect solution. There's a tendency sometimes to evaluate too soon. Can you tell me what the answer is while it's in this form? No, it's 0 over 0. So I have to physically remove the problem child, which is this guy. Now I can evaluate this guy. Don't write this down. Is there a problem here? The answer to the question is a scalar. I just showed the scalar equals the function, which is not true. In fact, there is no ordered pair where they're ever actually equal, believe it or not, because I canceled the discontinuity. But now this, I said, is equal to a scalar, which is even worse. A function does not equal a scalar, period, unless it's a horizontal line. So I just committed an egregious sin. Once you drop the limit, as you know, the next thing you write has to be the answer because you just evaluated the limit. That thing doesn't equal something else. You don't say my limit equals 5, which equals 10. Right? We agreed that wouldn't make any sense. So I can't drop the limit. Okay, second thing is, here's the second error that is often made, oops, as xy approaches. It's a minor thing, but it really does matter because it changes the meaning. Somebody might say, that's how I always do it. The limit of the function equals the limit of the limit. Here's what's understood about limits. Leave L'Hopital's rule out of this because that's the exception. Because L'Hopital's rule, you're saying the final results are equal, but the functions are never equal. When you apply L'Hopital's rule, the limit of the first thing and then the L'Hopital, those things are never equal, ever. It's the results that are equal. That's what makes L'Hopital special. When I write this statement, I am saying that this quantity is identical to this quantity always. Then I'm saying this quantity is identical to this quantity always, except at perhaps the place I'm evaluating. So when I write this limit equals this limit, then I am saying that this quotient is identically equal to 5/12 for all inputs. Is that correct? No, it's only true once. This quantity is never equal to 5/12. No, 5/12. This isn't even in the domain, so this quantity actually never is this, but its limit is this. Oh, remember, there's a hole there. So to say the function is identically equal to a scalar is a bad answer. That's never good. But this is a common mistake that people make in math all the time. I'm going to give you an example. If you were a tutor, I would hope that you fix this one because it can cause trouble down the road. All right, f of x equals x squared. I want you to evaluate at x equals 3. You're in a lower level algebra class. So then what do you probably write? F of x equals 9. Somebody tell me if you like that or don't like that and why. The first step, I'm saying y equals x squared. It's a parabola. What does the second one say? Y equals 9. That's a horizontal line. Those aren't even from the same universe. No. F of 3 is 9. F of x is most definitely not 9. F of x is x squared. F of 3 is 9. But if I equate the function with the scalar, if I write f of x equals 9, doesn't that mean f of x is 9 for every input? It's not a parabola anymore. That's why you don't equate functions with scalars. Functions evaluated you equate with scalars. The limit of the function is equal to the scalar. It's not equal to the limit of the scalar. So you don't, common error, and again, it's not life and death, but you don't want to say the limit of a function is the limit of the limit. Because then you're saying the function is identically equal to the limit for all input, which is, of course, not the case. I don't want to do that. That would be confusing. So in the second case, as soon as I drop the limit, I'm done. I've just evaluated. And that's the order of things. But algebraically, would you agree this is just not that bad? Now, going back to Calc 1, when you were doing limit problems, particularly when you had rational functions, if you could factor and cancel, you always did. You always factored and canceled. The only time you got D and E was like the one side of the limits weren't the same. You didn't get a lot of D and E's. But there were problems that could be D and E's, weird, crazy, warped. But in Calc 3, it's a little bit trickier. It's not always obvious. So let's look at an example of something, because I want to show you an alternate way, or an alternate problem, I should say. I have the limit as x, y goes to 0, 0. I'm going to keep it real simple. I've got x cubed plus y cubed over x cubed minus y cubed. I have a sum of cubes and a difference of cubes. Do those both factor, by the way? Will I have any common factors? That's not obvious. I'll go ahead and factor. How many have heard the acronym SOAP? I learned this from a student years ago. I loved it. What does SOAP mean? Do you remember?
No, I don't want to. Same, opposite, always positive.
Same, opposite. Okay, what goes here?
Always positive.
Always positive. Same, opposite, always positive. I love that. That is a way, by the way, it only works with sums and difference of cubes. But the best part about sums and difference of cubes is, in this case, all the coefficients were just ones and negative ones, but where the pluses and minuses go. Now, I've clearly factored this. Does anything cancel? First glance, you want to say yes, but does anything actually cancel? No. Okay, so kind of a dead end. This is approaching 0 over 0, and I don't get any cancellation. This is not a rule, but if you're looking at it and going, I don't know how I could possibly evaluate this. There's no algebra that I can see that's going to work. Then maybe see if it doesn't work. There's a tendency when there actually is a limit. A lot of people will try to prove the limit doesn't exist when it's like, no, if you just did some algebra, you'll get a really nice, happy answer. There's no algebra I can do on here. There's no factor and cancel. There's nothing that appears that I can do. So maybe this won't work. So I'm going to try a different approach. I'm actually going to see if I can prove it's not true. Now, there's something that's important mathematically. Can you prove a true statement is false? A true statement is false. Can you prove a true statement is false? No. Can you prove a false statement is true? No. What if you're not sure? Well, if something's true, how often does it have to be true?
Always.
If something's false, how often does it have to be false? So what's easier, to prove false or to prove true in general? Prove false, because you can always do it by counterexample. That's something in discrete math we spend a lot of time on. If something is true, you might not be able to prove it's true easily, because there might be an infinite number of cases, and oh my gosh. So then we use things like proof by contradiction. I'll start by assuming it's false, show I come to reach a contradiction. There's different cool avenues. I don't think that one's going to work. So I'm going to see if I can prove the limit doesn't exist. So what we're going to do is pick any path that goes through the origin, because that's where my limit is. This is our favorite one is 0, 0, because there's an infinite number of paths through the origin. I could choose, I'll give you an example. How do I choose multiple paths? I could say consider all paths of the form x to the n for a positive exponent n. Every parabola, cubic, even square root. Are there an infinite number of paths if I do this? Yes, that will work. Another one might be I consider every path linearly that goes through the origin, every possible line that goes through the origin on the xy plane. Are there an infinite number of paths here? Yes. What if? What if I chose an infinite number of paths and I got the same limit no matter what the path was? Does that prove the limit exists? No, because there's an infinite number of other paths. But it's a strong indicator that it probably does work. You just showed an infinite number of paths, gave you the same result. It's probably the case that that's going to be the answer. But if I choose one of these and I get different results, that proves the limit doesn't exist because different paths gave me different results. So the simplest algebraically, most people like this one. It's just easier. So I'm going to walk you through how to perform this. I'm going to say now, whatever this looks like in 3D, right? And there's my one fault line is the line y equal x, isn't it? Anything on the line y equal x is a problem. Had I picked any ordered pair other than 0, 0, or x and y being equal in general, if I picked anything else, this would be easy to evaluate. But I picked something on that fault line. So what I want to do is pick any path that goes to the origin, but not x equals 0, y equals 0, just in general, y equal mx. So we'll write it like this. Along the path y equals mx, and I'm going to put m is not 0. I'm sorry, m is not 1, sorry. Why can't m be 1? Because then I'd be y equals x, and that would be a problem child. So infinitely many paths, including 0, just as long as m isn't 1. Okay. So how do I do that? Go back to here, and this will be the limit as x comma mx approaches 0, 0. See what I did? I replaced y with mx. X cubed plus mx quantity cubed over x cubed minus mx quantity cubed. So this is what the limit looks like along that path. Along the path y equals mx, all my y values are mx. Hold off that for a moment. What's my numerator now? X cubed plus m cubed x cubed, x cubed minus m cubed x cubed. I only have one variable now. X is approaching 0 and mx is approaching 0. Doesn't that mean that x is approaching 0 is the only thing that's really happening right now? So can I just do that? Yeah, I only have x. There's no point in putting y as approaching 0. There's no more y in the problem. I replaced y with a scalar multiple of x. Oh. Well, it's still an indeterminate form, right? Everybody see that? It's still an indeterminate form. But every single term has an x cubed in it. Can I factor and cancel the x cubes? And by the way, you don't need to do it in your head. If you're not really comfortable with, I might make a mistake, just do this. X cubed times 1 plus m cubed. X cubed times 1 minus m cubed. Okay, so now what am I taking the limit of? 1 plus m cubed over 1 minus m cubed. You with me? We said m cannot be 1. M can be any real number other than 1. But m is a constant, isn't it? M is the slope of the line. And what's the limit of a constant? The constant. Oh. So it sure feels like, okay, then this has an answer. This is the limit. For every line passing through the origin, this is the limit. Hold that thought for a moment. Wait a minute. If m is 0, then this is equal to 1. What if m is 2? Then this is equal to 9 over negative 7. Oh, what if m is 3? Then this is 28 over negative 26. Oh, what if m is negative 1? Then this is 0 over 2, which is 0. Do you see that every real number m is going to give me a different result? Is that what I was looking for? Yeah, it's exactly what I was looking for. that means that multiple paths give me multiple limits. And if multiple paths give you multiple limits, then what is the limit? The any, does not exist. In Calc 1, we only had 2 possible routes. Now, the nice thing is I don't have to do something else. I don't have to, well, let's try something else. I just showed that different lines will give me different limits. So here's what you're going to say. Different values of m give different limits. Therefore, the limit does not exist. You really need to throw that statement in there. Before that statement, doesn't it appear that I just got an answer? Doesn't it appear that is my answer? Here's what a lot of folks will say. And the limit is 5, therefore the limit doesn't exist. Does that sound kind of like a goofy statement? The limit is 0, so the limit doesn't exist. Well, no, you just told me the limit. It can't be a number and not exist at the same time. The limit is 1 plus m squared over 1, or m cubed over 1 minus m cubed. Well, that sure looks like a limit to me. Oh, but wait a minute. If I have different values of m, this gives me a different result for every value of m. That's why the limit doesn't exist. Because this isn't a unique value. Oh, this is a value, it's just not going to be a unique value. Yeah, exactly.
If for all real values of m gives you the same limit, can you use that?
That's what I was saying earlier. Let's throw a what if. If I had tried this on the previous problem where the limit did in fact exist, if I tried to do multiple paths and I got the same value, that doesn't prove that that is the limit. But that is kind of overwhelming evidence that the limit probably exists, and now I should go ahead and attack it algebraically. Everybody understand? That's exactly what I was pointing out a moment ago. If I did this, and let's say I got, 6, that doesn't prove that that's the limit, but boy, that is overwhelming evidence. I just chose an infinite number of paths, and they all gave me the same number. I'm kind of thinking that maybe that's the answer. Now I need to go show it, okay? Because I can't prove it by example, but that would be overwhelming evidence that it's probably okay. The most common mistake people make in a problem is not this one. It's the first problem I did where the limit actually did exist, and we spend our time trying to prove it doesn't. That's not possible. If the limit exists, nothing you do can prove it doesn't exist. Now, where this one can be a little bit icky, what if I had said, actually, let me do this. One instead of 0, 0. Now the factor and cancel I could still try, but it's not going to factor and cancel because they didn't have common factors. And you wanted to do the multiple path thing. That's great. Can I still use this? It's not a trick question. Could I still use this if I want to do the multiple paths? No. Why? Because this doesn't pass through 1, 1. Okay, so what might I do in this case? In this case, I might want to do a path like this. Let y equal x to the n. N's got to be greater than 0. If n is, well, actually, no, take that out. That was only for 0. Does this pass through 1, 1? Yes, no, maybe?
Yes.
Yes. So if I wanted to do this problem, a common error that people make is they love the path through the origin. That's my favorite one too. But that only works if I'm approaching 0, 0. 1, 1, mx doesn't go through 1, 1. mx goes through 1, comma m, which is different for every value of m, but it's not 1, comma 1. Okay, so in this case, let's pick y equals x to the n. Then what would I do? I just wanted to set you up. Because this problem here is a little bit tricky. But it's the same reasoning. So I would say x comma x to the n approaches 1, comma 1 of x cubed plus x to the n cubed over x cubed minus x to the n cubed. Now I can go through the exact same way and
Question, can we instead say y minus 1 equals m times x minus 1?
Slow down, slow.
Can we instead say y minus 1 equals m times x minus 1?
Can I take equation of the line through? Yes, I can. Yeah, the question is, could I use point slope formula and do y minus 1 equals m x minus 1? Yes, I can. But what is it that I don't particularly love about this?
Cubing that.
What you said is absolutely perfect. But I got to cube that twice now. That would be my only reservation. Is that okay? You go, oh yeah, yeah. It is absolutely correct, and I will still get probably the same overall D&E kind of result. Just the algebra in that case would be kind of nasty. Would this be a fairly simple factor and cancel? Probably. So I'm gonna walk away from this one. Just the idea being, if you don't think it exists because you can't perform any algebra on it that you see works, okay, then pick a path that goes through the point in question, but a real general generic path. I can pick lines. Lines are the easiest to work with in general. Problem is when I have exponents, it can get a little bit nasty. That was the only thing, okay? So that's, evaluating the limit is necessary so I remember how to do limits in general, because the next day's lecture is going to be dependent on that I remember some basics of limits, just basics. And then we're not going to do limits again. Really, my goodness, you're really not going to do limits again anywhere, because you don't do any limits in differential equations or higher levels typically as much, because you take all your calculus rules that you've already developed. In this class, we do a little bit more limits when we're doing the Riemann sums for multiple integrals later, but it's going to feel just like Calc 1 stuff. It's not going to be anything, you know, tremendously difficult. Now, this process in general, can it get really difficult algebraically? Well, it can. Let me show you another one. Okay, Calc 1. We've done this one before. You guys probably did this one. If you're in my Calc 2 or Calc 1 class, you actually do this in the first day of the class. We're first learning how to do simple limits. Now, it's not quite a factor and cancel because it's not a rational function, but is this the indeterminate form 0 over 0? So that means that somehow or another, I should be able to cancel, well, something. What can I do to allow myself to... the x minus 4 is the problem, child.
Multiply top and bottom by root x plus 2.
So multiply top and bottom by the conjugate of the root term. Is this a legal move, by the way? Ooh, no one ever said that. What is the only thing you can never multiply or divide by? 0. So you can never multiply or divide by a quantity that can potentially equal 0. Is root x plus 2 in any danger of that?
No.
There's no value of x where that would ever be 0, right? It's always going to be at least 2. So that's totally legal, totally okay. In fact, that's the best move I could make. If I multiply top and bottom by root x minus 2, now I potentially have an issue that I may have introduced something that, you know, might not be there. But when I do this, by the way, when you're doing this, it's to create the factor, so don't multiply the bottom out, because then you're just going to have to refactor it later. What will my numerator be? Remember, a plus b times a minus b is always a squared minus b squared. So it's root x squared minus 2 squared. That's why you did that. Ah, okay. So that produces what? 1 over root x plus 2, which is no longer an indeterminate form. I can now evaluate that. So 1 over 2 plus 2, so 1/4. Now, you're going to see problems where you have the exact same situation, but now you have x's and y's, and you might have to conjugate. Remember, you're only going to do it if it starts off as an indeterminate form. Now, whenever you're multiplying top and bottom by something, you always have to be leery that the thing you're multiplying by, did it change it? If you guys can remember doing polar coordinates. Now, some of you, it wasn't that long ago, right? It was last month. When you were doing polar coordinates and you wanted to change something, and you went from rectangular to polar to rectangular, and you wanted to manipulate. I'm going to give you an example because this still applies and it still can cause us trouble. And Sam, you asked me a question the other day about the cone where I had the point missing in the middle. I have something of this nature, let's say. R equals, 4 cos theta. And I want to know what this looks like in XY world. Well, I can make a table of values and start plotting points. That's really inefficient, isn't it? And it's probably not very accurate. I love R squareds, and I love R sines and R cosines. So I would like to just multiply both sides by R. Can I automatically do that? I can if R equals 0 is already possible. Is there any value of theta that would make R 0? Tell me one. Pi over 2.
Yeah.
Do you all agree that if I replace theta with pi over 2, then R would be 0?
Yes.
So R equals 0 is already part of this. So multiplying both sides by R at this point would be totally legal. Then I'd get x squared plus y squared equals 4x. And then I can manipulate that and make it into a circle. Well, so why are you showing us on this, Brown? I really want to multiply both sides by R in order to figure out what this looks like. Can the right side ever be 0? No, the multiplying by R will completely change the nature of this. It won't be the same shape. Not a legal move. Ooh. Yeah, can't do it.
For these types of limit problems, if we get indeterminate form, can we still use L'Hopital's rule?
Well, you can on this one because it's one variable.
Yeah, but for the other?
Yeah, the other one because it's 2 variables. That's what I was saying. There's no L'Hopital's with 2 variables. Now, let's take your thought. What if I do the path thing? And I make it a path thing, so now I've actually changed my limit into a 1 variable problem down that path. But maybe by the way, when you're doing that, you should really never get stuck because you chose a path that made it happy and simple. But let's just say hypothetically. Could you use L'Hopital's rule on that path problem where you've made it a 1 variable problem? Yes, because you're doing a 1 variable limit. That you could, but the original question with 2 variables, you can't. There's no L'Hopital's rule for 2 variables because that only works when there's 1 independent variable. See, if I do L'Hopital's on an x, what do I do with the y? He says, unfortunately, it doesn't work. So I can't always do that. So when you're multiplying in general, you always have to be leery. But didn't you have problems in baby algebra where the only way you could solve the problem was to multiply both sides by a variable quantity? You had a quotient, you have variables in the bottom and equals, and the only way you can solve it is to multiply through. So then I would always say, and now put in the disclaimer. You see, could I multiply both sides by r now? Yes, as long as I did what? If I put in the disclaimer that r cannot be 0. Oh, because in algebra, you often had rational functions equal a constant. And you had to multiply both sides by the common denominator. And if you remember back to baby algebra, you sometimes got a solution that wasn't supposed to be there. And you go, what did I do wrong? This is my favorite problem to do. Many of you have seen this one before. Okay? The analogy is there's a classic Far Side comic. That was my favorite comic. Where the teacher's in front of the class, and the caption is, room of idiots. And he has a gigantic picture on the screen of a cow, and underneath it says cow, and he says, any questions, and everybody's hand is up. Like, what question could you possibly have? It's a picture of a cow, and it says cow, and everybody asks a question. So I had fun with that. So I'm going to write something mathematical on the board. X equals 2. Okay, any questions? All hands go up. No, x is 2. That's it. There's nothing interesting. Now, we know from the addition property of equality that whenever you have an equation and you add the same quantity to both sides, you will preserve the solution. And that's how we solve a lot of algebraic equations. We move things around. We also can multiply both sides by the same non-zero number, and we will preserve the solution. We do that all the time. So just for the heck of it, I'm going to multiply both sides by x. Okay? Now, let me add negative 2x to both sides. Okay, now let me factor both sides. Now let me solve. Okay. Wow, that was really exciting. I learned something today in Calc 3. Cow. How did I grow a 0? Did anybody catch that? I just did some really basic mathematics and x is 2. That's it. X isn't anything else. How did I get x equals 0? Because I just performed the ultimate illegal act mathematically. And a lot of us do this and we don't even realize it. I just did something that cannot be done mathematically. Did you catch what I did?
You changed the domain.
Not so much the domain, but I changed the solution. How? Wait, okay, let's go backwards. Well, clearly that came from here, and that clearly came from here. I said the multiplication property of equality simply states that if you multiply both sides of an equation by the same non-zero value, what did I multiply both sides by? X. Is there ever a time when x is 0? That's why x equals 0 is an extraneous solution. If I had multiplied both sides by x minus 4, you would have seen x equals 4 as a solution, because I just introduced it. I just said you can never multiply or divide by a quantity that can potentially be 0. Nobody multiplies both sides by 0 or divides by 0, but you might multiply or divide by a variable. That's why earlier when we canceled, we had to throw in the disclaimer because we removed something. We essentially divided by 0 otherwise. So I did a very illegal step, but a lot of times mathematically you have to do this. So when I multiply both sides by x, let's say for the purpose of whatever it is I'm trying to find, that was the only way I was going to find it was by multiplying. Then what I simply do is, and x is not 0. I just say, you throw in the disclaimer. So if I multiply both sides by any variable quantity, you just say, and that quantity can never be 0. Because at the end of the problem, it is not a guarantee that I'm going to get an extraneous solution, but it's a real possibility that I may. And the extraneous solution will be exactly the thing that equals 0, like I did in this case. So this always throws people like, how the heck did he get this? I'm in calculus, and I don't even see. What I usually tell people is like, I hypnotized all of you, and then while you were out, I changed all the numbers, and then snapped my fingers, and you're going, I just performed impossible mathematics, but it looked so easy. But it's the exact same thing. When you are doing things to a quantity, particularly indeterminate forms, if you go back to your L'Hopital's rule of limits, you sometimes had to manipulate things, and a lot of times you ask the question, is this a legal move? And in mathematics, if ever you ask that question, the answer might be, it is illegal, it's going to change your answer. So you just be mindful, or the easiest way out, you put the disclaimer. That's it. Okay, so the first section of new material is really about just introducing the concept of domain. That's really important, be able to state a domain. What is a level curve? What is a level surface? That's trivial algebra. And being able to take a limit, because tomorrow we're going to do limits. Now tomorrow we're also going to have some review. And so what I think I'd like to do tomorrow is perhaps start a little bit earlier. Again, I want to leave enough time for questions. There's only one thing that I don't want tomorrow, is that anybody leaves the room with unanswered questions. Now, the problem is some of you might come up with your questions later. Now, you need to have, the most important thing is that you will have attempted the practice test already before tomorrow. You actually have 2 practice tests. What's the second one? The quizzes. That's why I put the keys on there so you can retake them. Now, in a normal class situation, your first quiz might be a month before the exam. Here it's a week before. But it doesn't matter if you get 100% on a quiz the day you turn it in if you don't remember it the day of the exam. That's why it's really, really necessary to retake the quizzes, grade yourself, and say, okay, if I missed it, if I figured it out, and if I got it right, do I still remember it? It's less likely you're going to forget it, but because there's so much information, it's easy to get confused, right? It's easy to start mixing things up. I'm going to talk in detail about the exam, what you get to bring, what formulas, things like that. That's part of the review tomorrow, okay? So, just stay on top of things. So today and tomorrow's lecture is future material.
Will it affect us on the test if we're not able to go in early tomorrow?
I'm sorry.
Will it affect us on the test if we're not able to go early tomorrow?
No, I just want to allow a little bit more time. We could just stay longer. That's right. Okay. Let me give you. Would you rather start a little earlier, or would you rather stay a little longer? Let's say if we needed another 20 or 30 minutes, who would vote for earlier? Who would vote for staying longer? You're not helping me out here, folks. Okay, I'm going to let you guys arm wrestle. I'll probably end up doing a little bit of both. Okay, it doesn't make any difference to me. I just don't like people to walk into a test feeling like they've still got holes and, you know, if, most of you guys have been doing just exceptional work right now. I mean, the majority of all the quiz averages are, you know, well over 90% with, I don't know how, quite a few people over 100% because I throw a bonus here and there. It's just really phenomenal. Pardon me, it's like, I took them all out. Could you go ahead and stop recording?